Good afternoon, security tubers. In this presentation, we will be talking about API hooking from the user mode, and I would be concentrating on a specific mode of hooking called the import address table hooking, or the IAT hook. This is one of the basic hooks in the our hook toolkit. To understand this hook, we would be also using some time to understand the PE format. The PE format, or the the portable executable format, is the by de facto standard executable format of Windows, and it is documented in the WinNT header file. The most important concept to understand in this slide is that the image of a executable in the memory as well as in a hard disk remains the same, has been designed to remain exactly the same. To get this to be done, the creators of the portable executable format use something called a RVA, or relative virtual addressing. What does this mean? In simple terms, it is just an offset of an item inside the executable relative to the base address of the executable in the memory where it is being mapped to. This has been done because the compiler, when it is compiling or creating the executable, would not know where exactly, or the memory location where the exact executable will be loaded. So it creates something called an RVA, which is nothing but an offset to the base address. So if the base address is at a specific location, it says that the specific item location, or the import address table for example, would be at a specific location. So example we have taken, if the base address in which the executable is loaded is 4000 and the compiler says the RVA is 06, we could reach the intended item by adding 4000 and 6 together. We get 4006. Now that brings a very interesting topic to our mind, is how do we find out the base address, which is very simply done by running a function called get module handle and giving the name of the module that you want to get the base address of. If because we have done DLL injection, and which we have discussed in my previous video, you could send in a null parameter which would get us the base address of the function that is calling it, or the function in which we have injected already into. Let's start dissecting the PE format. It starts with a PE header. A PE header starts with a DOS stub. Every executable in a PE format has a DOS stub to inform that this program will not run in a DOS mode, and this is by de facto in every executable. The most interesting thing that we are interested in the DOS stub is the E_LFANEWA, which is a RVA, or the relative virtual addressing, to the NT header. Now NT header structure is made up of three members: signature, file header, and an optional header. The optional header, though it says optional, is no way optional but a very important RVA, which is basically linking the other very important sections of the executable. Sections. A portable executable is divided into multiple sections, like the .text, the .data, .bss, the IData, and multiple other sections. Some of the common sections are .text, .data, and BSS. The text is where the code is loaded, data is where the uninitialized data is stored, BSS is where the data is where the initialized data is stored, BSS is where the uninitialized and the global variables are stored, IData is where our intended import address table is stored, IData, as it says, is the place where the export address table is stored, which in simple terms means what are the functions exported by this specific executable. You are no way restricted by the text, data, or BSS segments. You could create your own segments by using the compiler directives pragma code_sec, pragma data_sec. The most important thing that we need to discuss in this slide is the PE import. If we want to call external functions into our executable, we could simply do it by copying the intended code into every location that we want this external function to execute. This is not an easy way, and this is not scalable. So the creators of the PE format made a method called the import address table, wherein the address of the intended function is written into the import address table when the executable is loaded by the loader program. And in the .text section, wherever your code requires this specific piece of code to be executed, it places a call to the location in the import address table, which will in turn jump to the exact function that has to be executed. Thereby, you don't have to copy the code every place. So with one call statement, you can execute this specific function multiple times of places. The example could be, you in your function you could be calling the printf functionality, which is now once the program loads the printf function, when the loader loads it, it finds out where the printf function is loaded and gets that address and stores it in the import address table, which could be used by our application to execute the printf functionality. Like I said, this call jumps to the import address table. What is an the IData section? The IData section is a collection of multiple image underscore import underscore descriptor structures. There are multiple there can be as many numbers of image import descriptors as many as the external executables that we link with. So if there are 10 different executables that our executable is linking with, there will be 10 image import descriptors. There is no limit to it, but we can find out the end of the structure by when we find a structure member which is filled with nulls. The two most important structure members are the characteristics or the original first thunk and the p image first thunk. Now if you look at this, this is the image import descriptor. If it has two members, characteristics and first thunk, both of them point to an array. The first thing points to an import address table, which is the most interesting topic for us, and the characteristics points to a hint name array. But the loader changes the address. Now if you look at it, the different functions like get message, load icon, translate message, is window, all these addresses are being stored in the import address table as well as in the hint name array. But the import address table values get changed or overwritten by the PE loader. So for our work also, we are going to work with this import address table. We're going to for our hook that we're going to place, we're going to change the address that is represented in the import address table with our own function, so that when a user calls the functionality and it jumps to the import address table, it will be in turn made to jump to our function. Now let's look at a small demo of what I have created. I have created a very small application. First I will run it without hooking so that you can understand what is happening. It gives out the current process and waits for me to give me a user input. I give in my name and immediately it pops out saying your name is Prasanna. It's a very simple application that I have created to show you the understanding of what we could achieve with a hook. Now let's run this again. Now idea is, here I have given out the process ID as 768. I'm going to inject into this process. I have already shown you in my previous video how to create a DLL injection. If you have not seen it, you could please go ahead and look it in the security tube website, where this video is also going to be posted. I'm just going to run my injector program, give it an argument of 768. Now I'm going to run the same program here, given the same values, Prasanna. Bam! Do you see that there is no message box that came in, because I have actually hooked into the message box functionality or message box function. And now what I have done is I have intercepted what arguments were sent, but this time you didn't see a message box, but you got a printf functionality saying that the value sent to the message box is Prasanna. So by this you can understand, you can not only change the way an executable works, you can even use a hook to understand the kind of parameters being sent and received by different functions. Now let's get to the code part of this one to understand what is happening. This is the piece of code that I have already written. This is actually a DLL code. which you would have understood from the DLL main. What is this basically is, this is the DLL that is getting injected into the intended program. So I am using this, I am using Visual 2005 to create my DLL. I have already declared a variable hooked, and it's a boolean variable, and I've declared it as false. So when my DLL main starts, it checks whether if it is not hooked. By default it is not going to be hooked. Then I do a set of declarations, which of this I would suggest look at the most important one are the module name and the function name. I have declared them because this is where this is the module and this is the function in which I am going to hook. So I am declaring it right now here, module name and function name. Then I get as I had told you, I am going to get the handle or the base address of the function. So we are going to use the function get module handle, send it a null, and store the result in a module HD, which it comes in a module H module. Then we get the actual address. We get the actual address of the get message box function by using a function called the get proc address. This is again a Win32 API function which brings in the actual address of the function. We store that in a variable called original function. Like I had suggested that the DOS header is the first part or the first section inside a PE executable. We are going to use the HT module and convert or cast it into P image underscore DOS underscore header. So basically what we are doing is we are getting the DOS header of the executable. Then we are verifying if it is a valid DOS header, because if it isn't a valid DOS header, we don't want to continue it. So we have put in multiple controls within this application, which you would see one by one. First thing is we check whether if it's a valid DOS signature. If it is a valid DOS signature, like I said, this emagic and image underscore DOS underscore signature, all these constants have been got from the WinNT header file. So if you want to do more work on the portable executable, I would suggest you go through the WinNT.h file to get more understanding. Like I got this image underscore DOS underscore signature constant from the header file. Next, we find out the NT header. Like I said, we have to go to the NT header. Now, if you see this, there is a make PTR and with some arguments to it. What is this make PTR? This is something from an idea that I have borrowed from a gentleman called Matt Pietrek. I'm sorry, Matt, if I have pronounced your name wrong. He is the gentleman who wrote the original paper peering into the Windows 32 portable executable format. What he is doing here is very simple. He has made a definition make PTR which takes in three parameters: cast, pointer, add value. And what he is doing with it is he's taking 2 pointers, add value and PTR, converting them into D words, adding them together and converting them into the cast that we are going to give it to it. So this is defined. We can use it anywhere in our program now. So first we use this to find out or jump into our NT header. Like I had suggested, everything inside a portable executable is connected through the base header plus the RVA. We know that the like I had suggested last time in my presentation, that E underscore L FANEW is an RVA to the NT header. What we are doing is we are going to add the base address which is stored in the DOS header and the E underscore L FANEW REV, and we cast this whole thing into image underscore NT headers. So now NT header has the NT header section. Next, like we had discussed, we are checking whether the signature is a valid NT signature. If yes, continue. Next, we come into the most important section, which is we are going into the from there we jump into the import section or the import descriptor structures. We get to the first import descriptor structures by adding the DOS header or the base header to the virtual address, which is part of the image descriptor entry array, which is pointed by the data directory, which is pointed by the optional header. Those sounds very cryptic. I would suggest if you could read a little bit about structures, arrays and pointers, you would understand what is being done here. We are doing nothing but getting the virtual address, which is a RVA, adding it to the DOS header here to get the image descriptor. Now we check, once we have this, we have the image descriptor, first image descriptor, or we are in the image descriptor section. Now once we are there, we want to check if there are any valid imports. We do this by checking if the import descriptor and the p image import descriptor NT header. So if we are basically at NT header, we cast it into import descriptor, and the RVA we calculated and stored it into the import description. If both of them are equal, basically that means there are no imports and there is no point in continuing with this function. If there are imports, we want to check, the first step what we want to do is find out the import descriptor for our specific executable or a specific function. Now if you understood, we had already defined that we are looking for this module name user32.dll. Okay, what we are doing here is we are saying inside the import descriptor, look for the member name. Then we are using the same function and getting the module name. We are getting the the idea from the I'm sorry for my thought process loss. We are getting the module name, which is stored in the import descriptor, and storing it into pz mod_mod name, and we are checking it with the mod name that we have already declared. If we find, we break. Once we break, what are we going to have? We're going to be stopping on the structure image import descriptor structure of the specific module that we intend to get. So once we get that, we are going to iterate through that, like I was saying. Once we find this import descriptor, we are going to iterate through this to get to the first thunk, get to this specific first thunk, then get to the import address table, which is what we are handling in this specific location. First, within this, you are getting the first thunk. So what we are doing is, in the p thunk, we are getting the first thunk and storing it in the thunk data. So you get to this first thunk, which is what is addressed in the line here. Inside this first thunk, we want to go to the import address table. We want to go to this import address table. How do we do that? We are going through each and every function. The p first thunk has a u1, and a u1 has a function name. u1 array, u1 is your array, and a member of that array is a function. Now function is the one that is storing the names of every function that is exported by this specific image import descriptor. Inside that, we are going to go in through a while loop. We are going to check if it matches with our function that we want to intend. We have already declared that we want to do it for our message box function. So what we are saying is, if you have the function name matches with the original name that we are intended, if it matches, you change the values. You change the value of the function to my function. We have already declared this function here, new message box, and this p thunk is going to go till you continue to find your function. Once it finishes, and it will go and change the address, it will change to this address here. What are we doing here? We are not doing anything here. I have just one important concept that you need to remember is that the call methodology, the method you call, there are multiple calls like the standard call, the CDECL call, the fast call. Microsoft, for most of its Windows API, uses the standard call. If anyone needs to understand more about the calling conventions, please write into me, and which I would give you in my last slide, my email address. I could make a video on the different calling conventions also. Like we discussed here, you have to match the exact call, because the function in which we are going to hook is going to call a function in a certain way. So we also have to match it in the same format. So you have to match the call. You have to match the arguments in number as well as in the proper data types in the way it is being called to. So you don't get up mixed up data. The idea is, if you replicate the exact function call, when it's being called, you will get the data in the exact format and you can do what you wish to like to do with it. So this function normal message box starts with the handle, then it takes a string, it takes a second string, then it takes a first string, a second string, and a type of button that you want. So you follow the same here for my new message box also. I'm saying I'm going to take an handle, then I'm going to string, I'm going to take the string, two strings, one string which is being message and the second string which will be your title, and then you have the button type. What I have done is I have taken the LP text or the text which is going to be shown in the message and said that the value you sent to the message box was LP text. I have not returned anything here. That is the reason why you did not see a message box. But if I was a malicious guy, I could return a message box here and the user would never know that there has been a hook and his data has been intercepted. And this could be done to any function that is called through an external function that is called by the executable. Now that pretty much concludes the coding part. What I would also like to discuss is I would like to start this again, inject into this again 5512, and I want to show you a specific tool that you could use to detect hooks on your machine. This tool is called Hook Explorer and it comes from a company called iDefense. I personally like this tool a lot. It can detect the IAT methodology of hook as well as a detour based or inline patching based hooks. The inline method hooks is something that I will be discussing in my next video. You hit on the application that you want to check, you hit on DLL test. Now if you look at this, this is where the magic is. This is where the original IAT is, which is at 427.2A4, but it says now it's being converted to this address, which is nothing but the start address of my function. It says this is the function that's been hooked, message box. It is not able to find out which process it's been hooked, but it says this is the module it's been hooked into. This is one reason why I like to use this tool. It's a personal tool that I keep using it on my machine. The one more thing that I would like to discuss with this specific methodology is that though it is very simple to implement this kind of a hook, this kind of hook is not very stealth, easily detectable and easily removable by the user, and this kind of hook can be easily bypassed. Like if you get back to our code, you understood I had discussed that if you use the get proc address, you would get the address of the function where it is loaded in memory. So if a user or a developer directly calls the get proc address rather than using the IAT, this hook would never be called, thereby bypassing the hook itself. Which is why I say this methodology is very easy to implement but very easy to bypass too. The next video that we will be discussing, the inline hook, is a very potent methodology wherein we will be modifying some the targeted function right when it is executing itself. So there is no way a user could bypass this, but this kind of hook also could be removed, but we will discuss all that in my second video. Thank you so much. Thank you, and this is my email ID as I had told. If anyone wants to discuss more about this hooks or the call methodology or anything to do, I would please write into me at prasanna.in@gmail.com and we could discuss further. Thank you.